Back in January, I was minding my own business in my favorite game, Pilgrammed, when suddenly, my friend proposed an interesting question. Yeah? What is it? Is it possible to make a potion of 25% or more melee damage for over 10 seconds? No, don't do this to me. No, don't do this to me. No. As a person who values this game more than my grades, of course I was on the case. So after quite a long time from my long-form videos, welcome back to Pilgrammed Math, where today we'll be talking about potions, but status level potions specifically, because splash potions are an entirely different field. But even if that's the case, there's still too much to learn. Anyway, during my experimentation of potions, I noticed something interesting. If you change the order you put modifiers in, you'd get two different results. Here we can see that when I drink this potion of a Rage Berry, Magma Slime, and Pink Slime, I get a number of 2.51. But now, if I drink this potion made from identical ingredients, I get a number of 2.22. So clearly there was something wrong here, and I had to find out what. To do this, I had to first understand how these modifiers affected the number. And thus, research began. In a potion, there are 4 fundamental things to realize. 1. The status level. 2. The effect name and effect. 3. The base ingredient. And 4. Duration. So let's take one Rage Berry for example. The status level refers to this number, so in this case the status level is 0.75. The effect name refers to the text above the status level, so right now it's strength. The effect is the buff or debuff tied to the effect name. So the effect name strength is tied to the effect X% melee damage and some strength buff. The base ingredient refers to the ingredients that gave the effect, which in this case would be Rage Berry. And duration is how long the potion lasts as stated by its description. So it's 12 here. It's really self-explanatory, honestly. So in this potion, our base ingredient is a Rage Berry, which gives the effect of 3.75% melee damage and 2+ strength, indicated by the effect name of strength, with the status level of 0.75, and finally a duration of 12 seconds. But actually, we can tie the concept of status level and effect together, since the status level impacts the effect. Now usually, the effect is proportional to the status level, but this may not always be the case. Anyway, the equation is unique to the effect name. So for example, the equation for strength to percentage melee damage isn't the same as metallic to defense. Using Rage Berries as an example, we can see that for each level of strength we have, we get 5% more melee damage. Whereas if we use metallic, we can see that for each level we have, we get 4 extra defense. With this information, we can plot how the status level impacts the effect for both strength and metallic, in which case we get these two equations. Okay, but what if you add multiple of the same base ingredient? What do you think happens to the status level and duration? If you answered that the original status level and duration are repeatedly summed up, no. It's actually modeled by an equation of straight line, but this time it's unique to the ingredient instead of the status level. Now, for example, 1 scrap metal gives a status level of 1 and a duration of 15 seconds, and 2 scrap metal gives a status level of 1.5 and a 22-second duration. For scrap metal, we can see that with linear regression, the equation for status level would be this, and duration would be this. And these two equations are consistent with 3, 4, and even 5 scrap metal. Whereas 1 Rockolio gives a status level of 2.25 and lasts for 15 seconds, and 2 Rockolios give a status level of 3 and the duration of 20 seconds. Thus, we would get these two equations for status level and duration for Rockolio. And if we compare to scrap metals, we can see that they're different. So despite giving the same effect name of metallic, they are modeled by different equations. So finally, with some mathematics, we can go back to modifiers and reverse engineer how everything works. So, what are modifiers? Well, I think the wiki has a pretty good definition on this, and that is that modifiers are defined as ingredients that modify the effects of the base ingredient. Now, according to the wiki, these include sulfur potions and splash potions, but I won't be talking about either of them in this video, so whenever I say modifiers, just think of magma slime, pink slime, green slime, blue slime, venom gland, and shrimp, which I'll be abbreviating with the first letter of the modifier. When a modifier is put, the status level is put through some function, let's call it f of x. An equation of straight line yields the best fit for most modifiers. But the numbers are kind of bad. To circumvent this problem, there are two options. You either round stuff off and pray for the best, or you can make use of a fact discovered by Subia52 on Discord, that metallic gives exact values. Since we know that for every one metallic you get 4 defense, we can reverse engineer the exact equations of f of x. Thus, we have these equations. Magma slime and pink slime were discovered by him, while I found the rest. With these equations in hand, one man, an ambitious man, decided to code a potion calculator. His name was Shower Please, and using his code, we can go back to our first example of 2 different status levels despite having the same modifier, same base ingredient. And we can see that it's because the 2 functions, m of x and p of x, have swapped positions. So this begs the question, what dictates this swap? And thus, I fell into the deep, dreadful pit of Pilgrammed Potion's function order. To start this perilous journey on the mind, I tested all possible combinations when the modifier amount is equal to 2, and their corresponding function. Thus, I present you with this data. The capital letters on the left signify the order I put them in from top to bottom. So MP means I put M first, then P. And the lowercase letters on the right represent their function order. So since it's PM, the function M would be applied first, then P. The placement of the base ingredient doesn't matter. You've probably noticed by now that M, P, and S all swap with each other. The same can be said for B, V, and G. However, notice that M, P, and S cannot swap with B, V, or G. Therefore, we can hypothesize that M, P, S may be regarded as a set, while B, V, G is another, different set. Let's call the set consisting of only MP as the externals, and GV as the internals. I've intentionally neglected B and S, and you better remember this because this will come up later. Anyway, I'll give you the data for all possible combinations with G, V, M, and P. Once again, capital letters represent the order I put them in from top to bottom, and the lowercase letters indicate the function order. Upon initial inspection, we can see that in the second slot, it is always occupied by an M or P, hence the name externals as they're the second to last function, whereas either G or V occupy the third slot, so they're called the internals. Let's assign a number to signify which slot they take. So the number of externals would be 2, and the number of internals would be 3. One key thing to note here is that modifiers of the same number can swap with each other. For example, M and P both have the number 2, so hence as you can see in the data, they can swap. Same goes for G and V. Now this interpretation will come in handy later. We can also see that the first external, read from left to right, is put in the second slot, while the first internal is put in the third slot. Now I'll pull up the data for B and S. You'll always notice that B is always in the first slot, so it is the outermost function, while S is always in the last slot, thus it is the innermost function. Let's assign B and S their numbers. B is equal to 1, and S is, as you could probably tell, there's a problem. what number can we assign s? Since s always occupies the last slot, technically speaking, its number changes according to the amount of modifiers we have. Not only that, but if we take a look back at our original data with only 2 different modifiers, we can see that b and s aren't always the outermost and innermost function respectively. To solve this, we must ask ourselves a simple question. What does it mean to assign the internals to the 3rd slot when the amount of slots is 2? That's when I decided I need to make a theory for a video game, and I'd call this theory modulo theory. Wait a minute. What do you mean the name's already been taken? Anyway, of course, since we're talking about the modulo theory, we're gonna need to introduce the star of the show, the modulo operator. Denoted with a percentage sign in programming, it returns the remainder when a dividend is divided by the divisor. You still remember what those words mean? Because neither do I. So, I'll go over them really quickly. Let's take 6 divided by 4 for example. 6 is the dividend because it is the number being divided. 4 is the divisor because it is the number dividing the dividend. And the remainder is this number down here, which would be 2. I know that technically speaking, if you express it in terms of a fraction, you can write 2 over 4 as 1 over 2. But don't do that because the remainder is 2 and not 1. So yeah, just take the original number you get. Now surprisingly, this shows up in everyday life, but probably not in the way you would expect. In what way though? Simple. Take a look at the time. Did you know that 12-hour clocks use the modulo function? For example, let's say it's 1 o'clock. On the clock, the hour hand would be pointing at 1. Waiting 8 hours gives us 9 o'clock because it's just conventional addition. But now, let's say we wait 13 hours. Thus, the hour hand would point at 10 o'clock. But earlier, we just added the numbers together to get 9. So why can't we add 13 to 9 to get 22? The reason for this is because numbers after 12 are sort of looped back, and the way to describe this mathematically is using the modulo function. Since there are only 12 numbers, we are working with modulo 12. So going back to our previous example, why don't we get 22? Well, here's the thing, we actually do get 22. Since we're working with a clock here, we need to notice that the numbers loop back after 12, so we need to consider the remainder of 22 divided by 12. And if we do just that, dividing 22 by 12, we can see that the remainder is 10, which, by the way, shares the same result as 10 being divided by 12. So since the remainders are the same, we say that they're equal in this scenario. Okay, but why are you telling me this? There doesn't seem to be any direct correlation here. Well, how about this? Let's lay 2 rules first. The first rule is that the modulo we're working with must always be an even number, so it must be either mod 2 or mod 4. Our second rule is that the modifier amount dictates what modulo we're working with. For example, if we have 2 modifiers, then we use mod 2. 4 modifiers, mod 4. But if it's 1 modifier or 3 modifiers, then we need to round that up to get 2 and 4 respectively. Now, with this simple definition, we can already explain why blue slime swaps occur in the first place. But before that, do you still remember what I said earlier? One key thing to note here is that modifiers of the same number can swap with each other. Now, this interpretation will come in handy later. For blue slime swaps to occur, that means one other modifier must share the same number as blue slime, which is 1. Since we know that the internals can swap with B when the modifier amount is 2, that means the internals must share the same number as B. So let's take BV for example. Firstly, let's establish what modulo we're working with. As you can probably see, we have 2 modifiers, so we're working with modulo 2. Next, let's consider the number of B. So we put 1 in the modulo function, and since we're working with modulo 2, we consider the remainder of 1 divided by 2, which is just 1. Then we consider V. We know that V has an assigned number of 3, so since we're working with modulo 2, we need to find the remainder of 3 divided by 2, or in other words, 3 mod 2, in which case our remainder would be 1. Now, since 1 modulo 2 and 3 modulo 2 both give the same result of 1, therefore, both b and v can swap with each other. We can also assign a number to s now. Since s is always in the last slot, that means with x amount of modifiers, it is always in the x slot. But x modulo x is the same as 0 modulo x, as x divided by x returns a remainder of 0. Hence, the number of s can be 0. Now, why can shrimp swap with the externals when the modifier amount is equal to 2? That's because we're working with modulo 2. 2 modulo 2 is 0. Therefore, they can have the same number and swap. Because of b and s's unique numbering, I'll be calling them miscellaneous modifiers. Note that they are not a set. But there's a scenario I've been neglecting this entire time, and it's that when MP or PM are put as the first two modifiers, when the modifier amount is larger than 2, the second external is considered first. I'm gonna be straight up with you, I have no idea why this happens, and I don't know how to explain it, at all. Anyway, next section. But what is the use of knowledge without the application of said knowledge? So in this section, I'll be going over how to determine the function order by just looking at the order you put them in the cauldron. Basically, there are 5 rules. Our first rule states that the modifier amount dictates what modulo we're working with, that the modulus must be even, and the number of slots is equal to the modulus. Our second rule would be that in a cauldron, the top modifier is considered first, and the bottom one is considered last. Our third rule is that the assigned number of a modifier after going through the modulo function represents the slot it is put into. For our fourth rule, if the slot the modifier was supposed to take up is already occupied, then it is placed in the remaining slots according to their order from top to bottom in a cauldron. As for our final rule, which is also our other problem, when MP or PM are put as the first two modifiers, and the modifier amount is more than 2, the second external is considered first. I bet I just said a ton of jargon that nobody understood, and since I don't really want any misinterpretations of what I just said, I'm going to give you guys some examples. Let's say my potion has the modifiers green slime, pink slime, venom gland, and magma slime put in that order, where green slime is put first and magma slime is last. So let's read this from left to right with reference to the rules. We have 4 modifiers, so we use mod 4. Our first modifier, G, is an internal, so it has the assigned number of 3. Put it in the modulo function and we get 3 mod 4, which is just 3, so we put it in the third slot as expected. Our second modifier is P, an external, with an assigned number of 2. So we put 2 in the modulo function, and since it's mod 4, we just get 2 again, so we put it in the second slot. Our third modifier is V, so we put its assigned number, 3, in the modulo function, and we get 3. But wait, the third slot has already been occupied by G, so we look at rule 4. Since this is the first time this has happened, out of the 2 remaining slots we have, which is the first and the fourth slot, we put it in the first empty slot. And finally, our final modifier is M. Now, we look at its assigned number and we put it in the modulo function. 2 modulo 4 is just 2, and we put it in the second slot, but it's already been occupied by P. Since this is the second time such a thing has happened, we need to look at the remaining slots. And since the only remaining slot is the final slot, we put it there. And hence, our function order is VPGM. Alright, now we're going to use a different example. Say I put MPBS in the cauldron. 4 modifiers, so mod 4. MP is first, so according to rule 5, we must consider the second modifier, p, first, and put it in the second slot, as it has an assigned number of 2 after going through the modulo function. Then, b goes first according to its number, and s goes to the last slot according to its number. Then we consider m. Know that m has an assigned number of 2 after going through the modulo function. But since p has already taken up that slot, we need to put it in the only remaining slot, which is the third slot. Hence the function order is bpms. The reason why we consider b and s before m is because that no matter what, the assigned number of blue slime and shrimp isn't shared by any other modifiers even after going through the modulo function. So we can just consider them first. Alright, next example. Let's say I put GSV in a cauldron. Now we have 3 modifiers, so we're working with mod 4, because the modulus must be even, and we need to round up the number if it's odd, so mod 4. And because it's mod 4, we have 4 slots. Now let's consider s first, and the reason why we can do this is because that s's number isn't shared by any other modifiers in this scenario, so let's just put it in the last slot according to its number. And we can consider g and v now. G goes first because it appears first, and by its number, we know that free mod 4 is still free, so we can just put it in the third slot. And we consider v. Since v shares the same number as g after going through the modulo function, that means we need to put it in the first remaining slot, in which case it would be the first slot. So our function order would be vgs. And for our last 2 examples, it'll be when the modifier amount is 2. Let's take MP for example. Now m appears first, so m goes into the second slot according to its number. And since m and p have the same number, we need to put p in the first remaining slot, which would be the first slot. So the function order of MP would be PM. The reason why the function order isn't MP is because of the final rule. So yeah. And for our last example, we'll use SV. Now S goes into the last slot, and V goes into the first slot because free mod 2 is just 1, so we put it there. And so the function order is VS. Anyway, I have a doc that shows the placement of modifiers as well as their corresponding function order. So if you ever want to test if your understanding on function order is correct, you can probably go take a look at that and see if your expected result matches up with the actual data. Okay, now that that's done with, we can move on to duration. Now, these are my equations for duration, and they're arranged in decreasing orders of confidence. So I have 100% confidence in my equation for green slime, but the same can't be said for venom gland. Now, why is there a confidence level in the first place? That's because if you actually measure the time taken, you'd notice that it would differ from the description by like 0.6 seconds to 1.2 seconds, which means we can't get a definitive reading of how long the duration of a potion is. In any case, these equations should serve as a good approximation for the actual result. Now, what if you want to calculate the resultant duration after adding multiple modifiers? Let's say my potion has both a green slime and a shrimp. Now, let's take the function for green slime's duration and put in 1 because that's how much green slime we have. Do the same for shrimps, and then you multiply everything together. So it's this, which gives us a duration of this. And all this brings us back to the question, is it possible to achieve 25% or higher melee damage for over 10 seconds? Well, I have discovered a truly marvelous proof of this, which this video is too short to contain. Just kidding, we will do a proof by exhaustion. Basically, using Shar's code, we can see that there are only 3 combinations that give a status level of 5 or above. Calculating their corresponding duration, and we get this. So as you can probably tell, none of them hold, and Thus, our question is answered. And that's pretty much Pilgrim's potions. Well, at least a part of it, the status level part. You have no idea how long this video took me. I found a counterexample to one of my previous theories, so I had to revise everything from like the beginning, and it was very, very painful. Major thanks to Shower Please for making the code. I don't think I would have done this as quickly without this code. It's so useful because I can just find out what the function order is instead of needing to test every individual case myself. I'd also like to thank Sumiya52 because he found out that metallic gave exact values, which made finding the equations much, much easier. I'd also like to thank Zuka for making the thumbnail. I know it's very goofy, but I believe that it works. Also Gravitas, he helped with data collection, and ZM, who also helped with data collection, but at the same time, he compiled a doc that listed the status levels and duration as you add more ingredients, which was incredibly useful because it wasn't on the wiki at that time. There's also XCY Gamer, or whatever this name is. She helped with giving a name to status level because I originally called it potency, which wasn't a good name. So yeah. And answer the question. Alright, goodbye.